as I continue work on this turret for Netanyahu, I'm starting to basically reprint some of the old parts from, many months ago with new, whiter, brighter, and smoother parts. Now, the problem with this is not inherent to reprinting parts, but I've run into a small issue, and that is balancing. See, in any mechanical system, especially one as sensitive as this, it is imperative that the structure of the rotational axis remains balanced. Otherwise, you run into a few problems. One key issue that I ran into is that, since this isn't really made of metal, it's mainly plastic, the tolerances aren't very strong, which means that even if I'm super accurate and super good, as I am, as per usual, it's gonna lead to unnecessary movements and unnecessary, wear and tear on the parts. Now, that isn't actually the main problem. The main issue is basically, so as you can see, there's definitely one side here that has a lot of the weight. So this motor weighs about 280 grams, plus the added weight of the gear structure on the left here. So with all that in combination, when the turret is rotated in such a way that basically makes the heavy part away from the small gear on the right, the imperfections in the structure actually lead it to tilt a little bit to the left, which means that the gears will actually slip, right? Which is not good. But in contrast, when the weight is above the gear, like this, then the weight is perfectly distributed, and now the gears mesh together very nicely. But obviously this can't happen, this can't be good, because the turret is going to rotate in any direction it wants, right? So we can't just limit it to being only rotating over the motor, right? That doesn't make any sense. So the obvious solution is to add counterbalances to the other side, which is going to be lighter than the side with the motor. Now we have to calculate some of the values here, okay? And that's the fun part, actually. But not really. It's not that fun. It's kind of boring. Now, as you can see from this image, this is the current prototype I'm working with. And now, obviously, this will be further refined, because it obviously doesn't look like the model I have done. That's mainly due to printing limitations, because each print, on average, takes about 5 to 10 hours. Because I kind of have a shitty printer, but that's besides the point. You can see I already added some counterbalances here, but first, let's calculate the current imbalance without the weights, so just assuming the left side weight. This line represents the rotational plane of the turret, and the yellow dot in the middle represents the center of rotation, or the axis. Object A1 is representative of the two bearings on the left side of the turret in this image. Additionally, it has a mass of MA1 and a distance from the rotational axis RA1. And the distance here is representative of the object's center of mass. And in this simulation, I've only decided to track the heaviest objects on the turret, because it would be a little bit tough to try and predict how heavy the plastic parts are, and their weight is probably negligible in this calculation. Here, object A2 is representative of the motor, which has a mass of MA2 and a distance from the axis of RA2. Object B here is representative of the bearing on the right side, which again has a mass of MB and a distance of RB. Now here are all of the static constants that I've measured out painstakingly. So MA1 is the two bearings, and since each bearing is 25 grams, the total is going to be 50 grams around. And the distance from the center was 7.5 centimeters. Same for MA2. The motor is around 280 grams, but since there's a lot of other parts in that area, I decided to round up to 300. And MB, so since the bearing is 25 grams, and you always gotta round up, right? So I just went to 30, and I measured it. It's 6 meters from the axis. Now we can replace these variable names with the values, and now we can calculate each object's moment vector. Here we'll use u for the moment vector for each object, and the general formula for any moment vector is the mass times distance times angle, but since the angles are already opposite, so perfect 180, we don't need to add that part. So here is just u of A1 equals the mass of A1 times the distance of A1, which is just going to be 50 times 7.5, which equals 375. Now for A2, same thing. So mass of A2 times distance of A2 is just going to be 300 times 4.5, which equals 1350. Same for UB, MB times RB, which is 30 times 6, which is 180. Now with the vectors of each object, we can calculate the total moment vector, and UB is minus because it is opposite of the other two objects. Then we must calculate the total mass of the system, which is going to be the mass of all objects now. And now to find the total radial offset, we must divide the moment vector by the total mass, which is going to result in a total offset of about 4.07 centimeters, pointing towards the right side. But obviously this is pretty terrible because if the offset is that high, you know, when it starts spinning, it's going to start wobbling a lot, right? So to counterbalance this, we need, you guessed it, a counterweight. Let's let object C equal the counterweight, so then MC is the mass of the counterweight, and RC is the distance from the axis. Now one thing to point out is that we actually know the RC value here, and it's 6 centimeters, and I'll tell you why. If you notice from this image, the counterweights are fixed in this position, and since we're measuring from the center of mass of the counterweights, that distance from the axis is already 6 centimeters. So in reality, we're only solving for the mass of the counterweights, or MC. Now we can set up the following equation, where we have to solve for MC. Now in order to make this balance, we have to assume U equals 0, because 0 divided by anything equals 0, which will result in a radial offset of 0. And once we plug in the values, we get a mass of 257.5 grams. This means that the needed counterbalance weight is equal to 257 grams. Now we can check our work by doing the first equation again, by adding all the values, and we can see that the RCM is equal to 0, which means that the counterweight pulls the center of mass back to the axis. Now, funny enough, the counterweights we have total to about 245 grams, so we're about, say, 12 grams short. So, in reality, if I had never done these calculations, I would have had the same result anyways, but I digress. But now it's time for the final test. Alright gang, check it out. So here we have the camera of the laser projection. So let's run the script. Okay, so currently it is moving. Alright, I had the screwdriver because it wasn't tight enough, the hole, so. But if we switch over to camera view here, we can see the laser projection. And it's actually IRL too. And let's like sort of sync it up with the mouse here. So as you can see, it's not synced up properly. Like it's not proportional to the mouse movement. But that's more of a sensitivity issue. And yeah, here we have it. Now, I've made some improvements over the last few days to the software. So I basically designed it in a way that the camera is actually mounted to the turret itself, not just like laying around somewhere. So as you can see, the laser right now is in the middle, and with this little Python script that I cooked up, you can see that it moves around according to the mouse delta. So I changed it up a little bit, and I honestly think this design is a lot better because you have a lot more versatility. You can rotate it wherever you want, you know, you're not restricted by the camera. And yeah, so this is probably the final version, and I will let you know that I'm working on something insane right now, okay? So I'm gonna put up an image on screen right now. This is the Radkampfwagen 90. It's a German light tank. And I'm basically making an inspired version of that with this turret. So I'm basically gonna design a tank base with like suspension and stuff with wheels with this mounted on it. So that's gonna be the latest, that's gonna be the next project, guys. So if you're interested in that, stay tuned, and I'll see you next time.